Hello everyone, this is Udayam, working as Assistant Professor in the Department of Mechanical Engineering, SJPIT, Bangalore. So today we are here in order to discuss about the subject called as Advanced Machining Science. So this subject is for the 4th semester students under Autonomous, and the subject code of this is 23 MEI 403. So the design of this syllabus is made in view of the students to learn about the advanced machining processes that occurs in the industries in day-to-day life. So it starts with the initial with the traditional machining and goes up to the non-traditional machining. And this is our department vision and mission statements. This is PSOs and PEOs, which is related to the program specific outcomes and educational objectives, and POs, which has been defined by NBA for engineering graduates, where the subject content is being mapped to this through the course outcomes. These are the references and the textbooks that has been used in order to make the notes material. So these are the objectives of the that you are learning. One, to make sure that it enriches the knowledge pertaining to relative motions, mechanical, required for various machine tools, to introduce students to different machine tools to produce components having different shape and size, to develop the knowledge on mechanics of machining process and the effect of various parameters on machining, and also to know various non conventional machining and hybrid machining processes. And these are the outcomes wherein which you will be understanding the basic principles of metal cutting, various machining parameters. You will be analyzing the properties and behavior of various materials during the cutting process. Also, you will be explained with the material removal mechanism associated with different advanced machining process, and also the advanced computer aided manufacturing software to design and simulate machining process. So the course syllabus. So this PPT is generally take you to Module 1, which is Introduction to Metal Cutting. So it has orthogonal and oblique cutting, classification of cutting tools, which consist of single and multi-point, the tool signature for a single point cutting tool, mechanism of orthogonal cutting, chip formation, shear angle, and its significance, merchant circuit diagram with problems related to it, and the basic requirements of tool materials, which deals with high speed steel, cemented carbide, ceramics, CBN, and diamond. All those things you'll be studying in this course. And here today, I'll be giving an overview of the first module. So orthogonal and oblique cutting. Okay, so as we all know that when we need to give a desired shape and size, okay, we use a tool, okay, which we call it as a cutting tool, and all the machines that involves in giving the shape and size to the given workpiece, okay, is called as machine tools. And to do that operation, we are going with the two basic cutting process. One is called as orthogonal, another one is called as oblique. So oblique cutting is a cutting process where the cutting edge of the tool is perpendicular to the direction of motion of the workpiece, and this cutting process is used to in turning and facing operations normally. And in orthogonal, the chip thickness is equal to the depth of cut, and the chip is typically thicker than in the oblique cutting. And in oblique cutting, on the other hand, is a cutting process where the cutting edge of the tool is at an angle to the direction of motion of the workpiece. This cutting process is usually used in operations such as milling and drilling operations. So where the tool rotates and moves in a circular or a spiral path in order to remove the material. And here the chip thickness is smaller than the depth of cut, and the chip is typically thinner than in orthogonal cutting. So the next slide will describe you the difference between the orthogonal and oblique cutting, and by looking into the sketch you can make the differences. So you'll get a sharp cut, and here you get an inclined cut. Here you have a single edge cutting edges that tries to take the materials normally during the turning and facing operations, whereas over here you will get a taper cut because the angle of the tool is inclined. It is not exactly perpendicular 90 degrees to it. And when you look into this, you have only two forces acting onto the cutting tool, whereas over here we have three forces that will be acting onto it. Okay, one will be the rotational force, axial force, tangential force, and the cutting force. Okay, so but the tool life of the orthogonal cutting is less when compared to that of oblique cutting, and only it has one cutting edge and it has more than one cutting edge in the action. So next we are coming across a single point cutting tool. Okay, because we will be focusing on the next chapter will be dealing with the various materials where the lathe, machines tools, where the lathe is the first machine, and in that machine we normally use a single point cutting tool in order to do the turning operations. So when we come across the single point cutting tool, if you look into the sketch, it describes the key components on a single point cutting tool, which includes a shank, face, end cutting edge is this part. This is the side cutting edge. This is the nose. The lower part of the nose or the side cutting edges we call it as flat. So normally we call this as a tool nomenclature. So the detailed explanation of this we can be carried out in a theoretical class. If you look into this, these are the major elements or the components you can see in the single point cutting tool. That is cutting edges, tool tip, rake angle, relief angle, and nose radiuses. So normally, if you look this angle, which is quite taper, in the other view also, you can say that it is inclined, which states that it is giving a clearance between the tool and the work interface. Okay, it is not coming in contact directly, which helps in increasing the tool life, right? So next one is the tool geometry. So uh, this are nothing but when it is being cut into three planes, x plane, y plane, and z plane, we get three different views of this single point cutting tool. So this top view, what you're seeing, you can see the two cutting edges when drawn normal to it. Okay, one is called as end cutting edge angle, and the one is called as side cutting and edge angles. When these two meets, we'll get a nose radius, and this is the part which is being used to do the cutting operation. So if you look into the another section of it, when it is being sliced in this profile, we get this view where in which rake angle acts the major part of it, which helps the sliding of the chip along the face of the tool away from the surface. And this is the relief angle from the side of it, okay, where the tool does not make the complete contact with the work interface. The other angle of this is this profile, which is the front view, okay, which I can show it in the next slides. Okay, where you see the lip angle, back rack angle, and the end clearance angle. This shank part is normally gets fixed into the tool post, but this face what you're going to see is normally used to do the cutting. So whenever you are being asked with the tool geometry, you'll be describing the angles of each and every part of the single point cutting tool, right? So this is the planes that is been cut across, where in which you can find the view. Okay, so when it is been sliced from the top, you can see the end cutting edge angle and side cutting edge angle, making a nose radius at the part, which helps in cutting. So we can detail explain this part in the theoretical class. Similarly, the another view of this when it is being cut in this plane when seen from the side. So this is a profile where in which you can see the back rack angle and the end relief angle forming over there. And in the next part, when it is being cut on the shorter length of it, you can see the side rack angle and end relief angle. All these angles has its own importance, which has been described in this PPT, but in detail we'll have it in the class. Right, so we have discussed about the process, cutting process, orthogonal and oblique cutting. Then we have discussed about single point cutting tool. So when it is being made to use, the material from the workpiece will be removed, and the form of material which is coming out to get the desired shape and size, and the waste of material from the workpiece, we call those as chips. Under this, you have different forms of chips. One is continuous chips. When normally this is being preferred, or you can say that when he is being used by the ductile materials, when it is been run at high speed and with minimal friction, you can observe this continuous chip formation on the workpiece, which helps in extended tool life, low friction, and decreased power consumption. But the disadvantage is the form of chips that is been formed is continuous, so it will be very difficult to dispose. Okay, so we use chip breakers on the tool face so that it helps in cutting off. Next one is discontinuous or segmented chips. That is, it does not form a continuous form of chip, but it is in the form of bits and pieces. This is majorly because of the brittle material that is being used over here. So whenever you use the brittle materials to cut, you will find the discontinuous chips. This helps in improved surface finish while using a brittle material, increase tool life and reduce power consumption. But the thing is, the surface finish when it is being used over the ductile materials will be rough, and that wear and tear will be more on this type of chips formation. Another one is continuous shift with built-up edges. Again, this is a continuous shift that has been formed, but when we look into the part of it, we see find the built-up edges that come across the chip interface in the tool, where the pieces of the chips gets welded to the surface and it gets joined along with it. There is a trouble in forming this because it may end up in rough textures on the tool faces. Next is a mature circle, where you have a different assumption that has to be made before going for the deriving part of various forces acting onto the workpiece, where the tool must be sharp. There should no contact between the cutting tool and the clearance edge, and the chip formation is a continuous one without any build-up edges. The thickness of uncut chip should be constant. The workpiece moves with uniform velocity during the cutting process, and the width of the workpiece is always lesser than that of cutting tool width. Shear occurs on the shear plane where the stresses is uniformly distributed. And this is the sketch that you will be drawing. Okay, you will be plotting it when the tool makes an interference where the chip is being formed along the shear plane. This is the cutting force that will be acting. This will be the tangential force, normal force. Okay, so we have different forms of force that will be generated when you're going to cut the workpiece onto the moving material. So related to this, where we have derived the equation for it step by step, which will be explained in detail in the theoretical class. And the last part of this module is cutting tool materials. But to possess this cutting tool materials, you need to keep in mind that there are certain properties that the material should have. One is the red hotness or the hot hardness, what we call. It is the ability of the material to retain its hardness at elevated temperature. It enables cutting tools to retain its shape and cutting efficiency. Toughness is the ability of the material to resist shocks or impact loads. Chemically, it should be stable. It should not react with other materials when it comes in contact. Shock resistance against high resistance for thermal and mechanical shocks, and low friction. If the material has a very low coefficient of friction, it will be better. It helps in increasing the life of the tool. So the different materials that we'll be discussing in detail in the class will be based on cutting tool, carbon tool steels, high speed steels, cemented carbide, and then at last ceramic, cubic nitride, and diamond. So this is put in order to make sure that, so whenever you are going with respect to temperature, when it is 250 degrees range of temperature, this kind of material can withstand. But if your cutting operations is exceeding more than 250, then we don't prefer to use carbon tool steels, but we go for HSS, which can sustain up to 600 degrees centigrades, and it can work up to 30 to 50 meter per minute of speed. But when it goes exceeds 1000 degrees, then we can go for cemented carbide, which can run up to 60 to 200 minutes per minute. And ceramic, which is much more harder material, which has high temperature resistance capacity, which can control up to 1800 degrees centigrade, and it can run up to 600 meters per minute of cutting speed. Next two are very costliest material, which we can say, where in which it has diamond and cubic nitride. Diamond is the first hardest material and the expensive among the all, and the next hardest material is cubic nitride, which is to be treated. Okay, so but this is advantageous, but expensive in nature. So I guess the things that is being covered is an overview of the first module. So in the coming classes, we will have a complete detailed description of all the things that we have stated. Thank you.